Hello everyone, my name is Ki-Hoon Moon and today we're going to present our project on phase characterization in steel using X-ray diffraction. In this presentation, I will explain the basic principle of XRD, how the machine works, and its application in identifying the different phases in steel. As you know, this technique is essential for material science, especially in understanding the crystalline structure of metals and alloys. Okay, let's get started about X-ray diffraction. It is a powerful analytical technique that allows us to study the atomic and the molecular structure of crystalline materials. In essence, in essence, when a beam of X-rays interact with the crystal lattice, the X-rays are diffracted by the regularly spaced atomic planes. And these diffraction patterns reveal the structures and identify the phase present and can even indicate impurities or strains in the materials. In our industry, XRD is used not only for phase identification in metals like steel, titanium, and aluminum, but also for assessing residual stress and performing microstructure analysis, such as examining grain size and crystallographic orientation. Next, take a closer look at how the XRD instrument works. The system essentially consists of an X-ray tube, which generates X-rays by accelerating electrons using a high voltage toward the metal anode. When these high-energy electrons strike the anode, they emit X-rays that are characteristic of the metal used, commonly used the copper. And these X-rays then hit the sample, and as they interact with the crystal lattice, and they are diffracted at specific angles. The detector collects these diffracted rays, and by analyzing the intensity distribution over a range of angles, we can determine the key properties like the lattice parameters and phase composition like that. So this information is crucial for both research and quality control in material engineering. Next, this is a fundamental principle governing XRD and Bragg's law. This law is expressed by the equation n lambda equal to the sine theta. And here n is an integral representing the order of the reflection. The lambda is the wavelength of the incident X-rays. D is in the planar spacing in the crystal, and last theta is the incident angle. When X-rays hit the crystal planes at the correct angle, constructive interference occurs, and that is the waves reflected from the different planes aligning phase. This condition creates a detectable diffraction peak, which allows us to infer the spacing between the planes and thus the crystal structure, especially by rotating the sample and recording the diffraction pattern. We can generate a complete map of its atomic arrangement.
A good starting point for looking into phase identification of steel alloys is to start with the FEC phase diagram. If you look at the phase diagram, you'll see that in the 0 to 2 carbon weight percentage range, you have what is typically called steels. For these steels, the decomposition, the controlled decomposition of the austenite, the gamma phase, into ferrite and cementite is typically what you're after. However, not all the phases of steel that are relevant for engineering purposes appear from thermodynamic equilibrium that we can see in the phase diagram. In many contexts, we actually have to both characterize and control the presence of metastable phases that we typically acquire from some kind of treatment of the steel alloy. And so a good starting point for looking at how we can decompose austenite into different other phases, we'll see here at the TTT diagram that for different cooling rates, we can obtain either the equilibrium pearlite phase, that is the decomposition into ferrite and cementite, or metastable phases such as bainite and martensite, which also have relevant engineering applications. So just to reiterate, that is, we can attain these equilibrium phases by processing. So we can perform hot or cold work as well as in combination with some kind of specialized heat treatment. And these are all practically useful. Um, and controlling and characterizing these different phases in your steel will then be critical for understanding your mechanical properties that you get out of it in the end. If we take a slightly more narrow look at the martensitic phase that occurs on quenching, you can see that by looking at the figure on the right here, you can see that based on the carbon content, you're going to get different martensitic phases present in your steel. For a low carbon content steel, as you see here, between 0 and 0.6 weight%, you typically get lath martensite, whereas for a steel with a carbon content above 1 weight%, you will typically get a pure plate martensitic transformation by twinning. And if you have an intermediate amount of carbon, so a medium carbon steel, you will see a mix of phases of both lath, plate, and in some cases also the retained austenite phases in your steel. And so in that case, to be able to quantify how much do I have of each phase can be critical for your application. Just to show here on the left, you can see that in figure A that we have the microstructure of a oil quenched steel. And then you can see here in image B that we have a few packets of lath martensite in this image here. And on the two bottom images, C and D, you'll see the plate morphology of martensite. And so one way to characterize this kind of martensitic steel is by using XRD methods. And in this specific case, we have a research paper where some researchers use a novel XRD method that consists of peak fitting of these martensite peaks that occur in order to break down the peaks into both the lath and the plate subpeaks and measure their contribution. And what they do is that in this method, they essentially back calculate the lattice constant ratio for the A and the C lattice constant for the tetragonal unit cell, and then use that to back calculate the carbon content. And knowing the carbon content then gives us information about what we can expect in terms of the mechanical properties of the steel. And what this shows is that you can use the XRD method specifically to increase the granularity of your steel phase identification in addition to performing routine phase analysis of your steel.
Besides the XRD experiment from the literature review, we also did XRD experiments on our own steel sample we have on site. The material we're using is the recycled steel powders provided by Asgard Metal. They are the only spray forming facility around the world. We did experiments on different kinds of steels. We have stainless steel 440C, cold work D2, hot work H13, and high-speed T15. Basically, all of these steels besides H13 are high carbon steel, and the powder size for all of these materials ranges from 65 micron to 150 micron. And all of these powders are overspray powders collected during the spray forming process. Our setup for the XRD experiment, we were using the copper radiation, where K alpha 1 is 1.540598 for wavelengths, and the wavelengths for K alpha 2 is 1.544426. And the voltage we applied here was 45 kilovolts, and the acceleration current is 40 milliampere. And the scanning angle we did on the for the experiment was from 30 to 125 degree, and the step size is 0.03 degree, and the counting time is 10 seconds. Here is X-ray diffraction pattern for all of our testing material. For T15, it stays mainly austenitic with small fraction of ferrite or martensite, and also a small fraction of tungsten carbides. For H13, it's mainly ferritic or martensitic, and also a small fraction of retained austenite. For D2 and 440C, they're fully austenitic. However, for all of these materials, they're supposed to be martensitic steel. So D2 and 440C remain fully austenitic during spray forming process and also the collection process, which make these materials very special.
And so in conclusion, we see that XRD is a powerful and versatile method for phase identification in steels. And it can be used both for your routine phase analysis when you're using or making steel in any kind of engineering application, as well as try to use some more novel XRD methodologies, including peak fitting, to characterize the steels. And overall, it helps us to understand the material response to either mechanical deformation and heat treatments, and therefore allows us to more accurately quantify both the phases and the properties of the steel.